So this module is going to be a little bit mathematically heavy, and for people who are not interested in the deep mathematics of this variational method, you can very well skip it. But for people who wanted to know a little bit more about how to apply this variational method for various applications and see the mathematics behind it, we are going to look into the method of weighted residuals, which will also be very fundamental for us to understand the method of moments, which we'll look into at later stages. So without further ado, let's look into the method of weighted residuals. Similar to the basis functions which we have used, earlier case we used the v of n as the basis function. We are going to choose a new set of function which is called as the weighting function. And the weighting function is written with w, and the basis functions are written with v of n. So we start with the linear inhomogeneous equation and calculate the inner product with this weighting function on the both sides. Here we have the test both sides with, we are testing both sides with v of n. So what we are doing here is, remember our first equation is L of u is equal to g, and u is written as sum of certain a of n, v of n, and certain number going from 1 to n, and we have g which is the given forcing function, it is known. So what we are doing is, we are taking the value a of n, v of n, and we are bringing the operator L inside the summation. So we are starting with L of u, a of n, v of n is equal to g, and we are bringing this L inside the summation, and that is what we see here in this particular slide. So where we have the L inside the summation, and we are testing it in the sense we are doing the inner product of w of m on both sides. So remember, the inner product is in a way testing the similarity between both of these things in one way or the other. When the inner product is equal to 0, I said that they are orthogonal. When they are similar, the number will be a very large number, and when they are in between, that means they are in between orthogonal and similar. Similarly, this is also done on the right hand side. So we can take out the summation out, and what we will get is, we will take out the summation and expansion functions out. So it will be inner product between Wm of x comma L of v of n of x is equal to the right hand side, and this equation can be written in the matrix form as follows. So what we have got here is this a of n, which is a vector which is coming from here, and z of mn, which is nothing but this particular inner product term, which is a matrix of size m comma n, because it has m and n here, and then the right hand side, which is again a vector which is purely dependent on m. So when we are expanding this, we will see what we will get is the terms as follows. This is the starting point where we say the method of weighted residual is, we are weighing it with respect to a test function, and we are doing the testing on both sides. How are we going to go from this point to the Galerkin method is a very simple assumption. The assumption is, when I say when the w terms are same as the basis function. So remember, these are the basis functions which I use to expand my unknown, and these are the weighing functions I am going to use as a testing function on the left and right hand side. But when I say they are both same, I fall into a method called Galerkin method. It is due to one of the greatest mathematician from the Russian Republic, who has contributed enormous amount of techniques and tools to applied mathematics, and this is one of his classical examples where he has just said by using the weighing function and the testing function, or the weighing function and the basis function to be same, we end up into a very simple form. So the matrix becomes very simple, as in the slide here, where we got the left hand side as only in terms of Wm. So we can say Wm is equal to V of n. So the terms will become very simply only as a function of V of m. So remember, in the old case our left hand side was a function of W and V, but here we say we are having them both same, so you will have only V on both in the first and the second term. And also on the right hand side, instead of W we will have the basis functions V of m. So Galerkin method to find a solution to a linear inhomogeneous problem is simply starting with the initial PDE, and we are expanding it using the set of basis function, like in the case before, where we say our initial set of values are given by the basis function u is equal to sigma n a of n v of n, and we are just bringing the L inside the summation, and we will have a simple equation given as follows, and from here we can test both sides using the basis function itself, and we end up in a very simple form. So remember, we are saying the weighing function and the basis function are the same, so we have only the basis function on both sides, and we end up in a very simple matrix form as follows. So what we have done so far is we have given you the logic behind the method of weighted residual and how we can go from method of weighted residual to the method of Galerkin, and with that we are coming to a very nice stop. But before going to a stop, what I would also like to do is a very simple example, because we started with the action principle, and from the action principle we are going into the PDE or the Euler equation. You remember how I derived it in the earlier modules, but I would also like to look into how to derive the functional starting with the PDE itself. So this will be a kind of an exercise which I would like to do in this particular module before we break. So that will kind of get you an understanding how we can go from a PDE to the functional, and also starting from a functional to a PDE. So both ways we are covering the main points. So with that being said, let's look into a simple example where we start with the functional from a PDE. So let's assume that we have been given a particular PDE which is written of the form, let's say a Poisson equation, where we have the Laplacian on the potential is equal to, so I will take the minus of the Laplacian, is equal to some forcing function g. The reason I am taking a minus is because of making the operator L as positive definite. So positive definite is a fundamental requirement on the operator itself, and if the operator L should be positive definite, so when we operate the operator, the inner product, so we will get a value that is more than 0. So that's the definition of the operator being positive definite, and if the operator is positive definite, the solution to this particular problem will be unique. So the reason why I have put a minus here will make the operator L is equal to minus square as a positive definite operator. So that's the reason for this minus. it's not that important, but it's important for you to know the reason behind it. So the reason behind it is to get a nice function and the uniqueness of the solution. So let's start with this Laplace equation where we have got minus equal to g. I say L is equal to minus of this, so my expression will be L of phi is equal to g. So this will be my starting point where this is the PDE for which I want the functional. The functional for this particular PDE. So the first step of doing this is I have to multiply this particular PDE with a particular variation, and that's what I am going to do in the step 1. So step 1, as you can see in the slide, multiply this particular PDE with a variation written as delta phi of the dependent variable phi, and I am integrating it over the domain. And the second step is I will use the divergence theorem or integration by parts, either of them, because they both lead to transferring the derivatives to the variation itself, because I don't want the derivatives to sit on very difficult expressions, so I wanted to transfer them to the variation itself so it becomes mathematically easy. And then the step 3 is I apply the boundary conditions on those terms and I bring out the variation operator outside so as to get the final functional. So I am going to do this on this particular expression. I said I am going to set the value of L as this, and the minus sign is taken on the other side. So I am doing the first operation. I am going to multiply by a small variation. So and then I am integrating it over the entire domain. So let's do this step by step so that it will be clear how I have arrived to this point. So now we will take a simple Poisson equation and do a little bit of mathematics. It's going to be a little bit tough, but if you follow and stay with me, I think we will get to the final expression. So let's start with this expression given by L of phi is equal to minus g of x comma y, and then L here is the Poisson operator, so we say is equal to minus g of x comma y. I take it to the left hand side and I say minus square phi minus g of x comma y is equal to 0. So this is my starting point, and I am going to multiply this expression with a small variation of phi, and I am going to integrate it over. So I am going to put this expression here, and then I am integrating it over the surface. So this is a 2-dimensional surface. I have a 2-dimensional integration, so x comma y, and then I will have dx and dy, and the left hand side will be equal to 0. So when I put this expression here, you will get to the point where we have the form, and I say that is the small variation in I is equal to the double integration minus square phi minus g with a small variation in phi dx dy is equal to 0. I say this is this expression of del of I because I have a small variation. My assumption is this particular expression, when I do it step by step and take out the del out of the expression, I will get to the functional what I am interested in, and I have assumed that that functional will be called as I, so I have an I here. So this I can expand equal to the double integral, I will take the minus out, del square phi dou phi dx dy minus double integral g of dou phi dx dy. So this is the basic expression, and this expression is equal to the value I have given. So this is the step number 1. So in the step number 2, what I am doing is I am going to apply either integration by parts, or I can apply the divergence theorem. So I will use the integration by parts so as to transfer the derivatives onto the small variation itself. So my idea is to change the derivative from the higher order derivatives directly on the small variation. So I am doing the integration by parts to get to the point where I say that's equal to, so let's say my first integration by part will be minus integral d by dx d phi by dx small variation times dx by dy. So this is, I am just changing the way it has been written, and what I am going to get is the next expression, which is this is equal to minus integral small variation d phi by dx minus integral partial differentiation with respect to x d phi by dx the small variation times dx. So in the step 2, what I have done is I have done the integration by parts to split the term from the initial point. So in order to take the higher order derivatives from here directly on the phi, so I have arrived to a point of writing it like this. So in the step 3 and step 4, what I am going to do is I am going to apply the boundary conditions, but for that I need to derive to the point. So what I will have is d phi of I is equal to the two derivatives. So remember that I have applied on the integration by parts to get these two expressions. This expression is the way to get from integral u dv. So this is integral u dv is equal to uv minus integral v du. So this is the integration by parts. I am applying that integration by parts on my initial expression of the small variation on this particular integral. So what I will get is, applying the integration by parts, I will get an expression which is similar to this: partial differentiation with respect to x, partial differentiation with respect to x again of phi plus d phi by dy d by dy phi minus dg phi with multiplied by dx dy minus integral the small variation multiplied by the partial differentiation with respect to x dy minus the same thing with respect to x. So remember, this is the terms directly coming from the del square term. So these are the terms that are directly coming from the del square term. Since we are only in 2 dimension, we have only 2 differentiations, second order differentiations, and applying the integral u dv is equal to uv minus integral v du, we are getting to this point. Now what we can do is we can take out the del outside of the equation to write this entire expression in a simplified form. So what we will have is del is equal to, so I will take out the entire equation del outside, and then I will have an integration where I will have 1 by 2 d phi by dx square plus d phi by dy square minus 2g phi dx dy, and we will have the term, we will have these two terms coming into the play, which will be minus del integral phi d phi by dx dy minus del integral phi d phi by dy dx. So what I have done here is I have taken out the del out of this particular expression. In the initial expression what I have got is the del term was always inside, and I have taken the del term outside the expression to derive a form which will be having del terms outside the integration. So now I can apply the Dirichlet and Neumann boundary condition. Remember, these terms are the boundary condition terms, and if we say that we are talking about a homogeneous boundary condition, so these terms will be equal to 0. So the Neumann boundary condition will define the function's normal derivative will be equal to 0. So we will have only the term which is here. So what we will have is, we will have a term which will only contain this particular thing. So we can write them as is equal to by 2 integration square plus square minus 2g phi dx dy. This is applying Neumann boundary condition. So these terms are going to 0, so you will have only this term. So I have taken the del out, so basically I have a functional, so this del and del gets cancelled, so what I have is an I which will be the value of the I. So this is because of this. So when I apply the, when I look at the symmetry of this left hand side and right hand side, what I will have is I is equal to half integral. So instead of writing the equation like this, I can simplify by saying d phi is equal to and dy is equal to, so when I apply that I can write the expression in a simplified notation as x square d y square minus 2 phi g dx dy. So this is the final expression of the functional. Remember, in the initial case when we talked about the work of Michelin, which gave us the expression of I as comma phi minus 2 comma g. So this is a very simple similar case where we have got inner product term which is basically given by this term, and you have got this term which is basically given by this particular term. So what we have arrived now is basically, we said we start with the simple PDE and we have arrived to the functional. It has been mathematically a little bit too complex, but I think step by step we have seen how to get to it. So you can follow it and do it also on other PDEs. So let's summarize what we have seen now in the form of a slide here. So we started with the Poisson equation and we said we will do the step 1 where we are multiplying with a small variation which is given by this particular term, and this is equal to 0, and we call this particular integration as del of I, and we are splitting the terms, taking the bracket out, and then we are going and applying step 2 where we are using integration by parts. Remember I said this is integral u dv equal to uv minus integral v du, and this is exactly what you are applying here on this particular expression, and we get terms which are the main terms and the terms which are related to the boundary terms. So when you apply the boundary conditions, these later terms will disappear. So we can take out the del out of the bracket and we write the entire expression in a form will have del outside the integration. By doing that and applying the Neumann and Dirichlet boundary condition, we can basically reduce this equation into only the main terms without the boundary terms, and finally seeing the left hand side and right hand side, the del terms get cancelled, so you get only the I term which is given by this particular expression. And finally we saw that this is very similar to what we have seen before. So in applying any of these methods to partial differential equation, the boundary conditions are integral part of the problem itself, because a problem will be ill-posed without a boundary condition. So in a boundary condition, when we say it could be a simple Dirichlet boundary condition or Neumann boundary condition, where we can say it has a value equal to 0 or some value, so it could be homogeneous or inhomogeneous condition. So the integral part of the problem is the boundary condition as well. So in this particular approach, when we are applying step 1, step 2, step 3 to arrive to the functional from the PDE, applying the boundary conditions, we are able to simplify the expression further. Basically the boundary conditions are enabling us to reduce the terms and directly go to the functional term, and also the boundary conditions are given as part of the initial PDE itself. So when we use those boundary conditions, we are able to get to the direct functional step by step. So we have looked into a really heavy mathematical journey. I think it's worth it if you follow it and appreciate the mathematics behind it. So in the next modules we will look into finite element method, and we will investigate more how this finite element method is applied for various electromagnetic problems. We will look into a lot of simulations as well, so don't think it's going to be only mathematics. It's going to be a lot of application and simulation using MATLAB. With that, I would say we'll end here in this module, and we will see you in the next module. Thank you.